Hello everyone. Today I am going to explain about the CMOS fabrication by using twin well process or TwinTub process. Okay. So in the previous discussion I have explained N well and as well as P well process for the CMOS fabrication. Okay. So today I am going with this TwinTub process. Okay. So in this TwinTub process, so what is the advantage of this TwinTub process as compared with the N well and at the same time P well process? Okay, so here it is very advanced technology in the fabrication of CMOS, and the second one is here both NMOS transistor and PMOS transistor will be optimized separately. Okay, that means they are separated. So here we have introduced two wells, N well and P well. Okay, in the previous discussion, if it is a N well process, only we will place that N well, and if it is a P well process, we will place only P well. But here it is not the case. Here we are placing both N well and P well. Okay, that means what? For PMOS and NMOS, we are separate wells. Okay, so because of that, it is called as twin well or twin tub. Okay. N well and P well, right? So that is another advantage, and at the same time here whatever the transistor parameters we have for the PMOS, NMOS, we have for that is threshold voltage and body effect, and at the same time channel conductance, trans conductance, all these parameters are separately we can place or we can give separately for these transistors. Okay, so those are the advantages here we have. So now I am going with step by step how we can fabricate CMOS by using our twin well process or TwinTub process. So in the step 1, what we will consider? I will consider first N type or P type substrate. Okay, so N substrate or P substrate, anyone can take, but generally we will take N substrate. Onto that N substrate, what we will do is we will place a pure silicon crystal layer. Okay, a pure silicon crystal layer called epitaxy layer. Okay, so that epitaxy layer formation will be done, and that is by using epitaxy process. Okay, so that is the first step. So here I am taking the N substrate. Above that, what I am doing here, consider the N substrate silicon wafer and grown a pure silicon crystal layer. Okay. So grown a pure silicon crystal. Pure silicon means it has high resistance. Okay, pure silicon crystal layer using epitaxy process. Okay, so I have introduced this epitaxy process also while explaining about the fabrication of IC. So the next step is what? Epitaxy process. By using epitaxy process, I am placing an epitaxy layer above that and substrate wafer. Okay, silicon wafer. So that is epitaxy layer. Epi means here above and taxy means in a order. Okay, so in a order, right? So that is epitaxy means. So by using epitaxy process, so I am placing epitaxy layer. I am growing an epitaxy layer on the N substrate wave. Okay, silicon substrate wave, right? That is the first step what we have. So this is epitaxy layer region and this one is the N substrate. Okay, so after this step as usual, so what we followed for NMOS fabrication, PMOS fabrication and N well process and P well process. So next step is what? Oxidation process. Okay, so after oxidation, what we are going to do? After oxidation we are placing a photoresist. Okay, so that's what I am going to do here. So grown SiO2 layer above that epitaxy layer, and above that SiO2 layer I have to place the photoresist. Okay, so by using the oxidation process, here I am growing this SiO2 layer. Above that I am placing my photoresist. Okay, so I already told that photoresist is in liquid form. If you place that liquid at one place and if you spin that, equally distributed. Okay, so that is what? Photoresist. This is the second step what I have. So grown SiO2 layer above epitaxy by using the oxidation process. And after that, what we have to place the photoresist above it. Okay, so this is the normal process what we have done for previous N-well and P-well process, and at the same time N-mass fabrication and P-mass fabrication. So after this one, what I have to do? Okay, so here it is the very important step in TwinTub process or tin well process. So we require two wells. One is N well and another one is P well. Okay, then how we can form? Okay, so after formation of the photoresist, so we will place or we will expose that photoresist to the UV light by using the mask, and here we require N well and P well. So at two places I don't place this light on the photoresist. Okay, like that I will prepare the mask. So here I am using the mask here in the next step. So apply the UV light using mask for the formation of P well and N well. Okay, so what we are going to do here, by using the P well and N well. Okay, so by using the mask, so I am going to form that. Okay, using photolithography. So already we have seen photolithography. That is nothing but first we will prepare a mask, and after that preparing a mask that will be transferred onto the glass. By using that glass mask, we will send the UV light or we will expose that photoresist to the UV light. So that's what photolithography means here. I already mentioned this one in the fabrication process. Okay, so now what I am using here, this is the mask I have prepared to form the or to define the regions of P well and N well. So here I am defining the P well and N well. So here this whatever the coating that is there, black coating here and here, it will blocks the UV light and the remaining areas will be exposed to the UV light. So that is the step. Apply UV light by using the mask for the formation of P well and N well by using the lithography, photolithography. Okay. So now if I send this light, this is the UV light what we have. This is the UV light and this is epitaxy layer. And this is N substrate, what we have considered. Okay, now what I am doing is I am placing the light, I am sending the light through the mask. So from this point to this point, this photoresist is exposed to the UV light, and this point to this point, this is exposed to the UV light, and from this point to this point also, the photoresist wherever that is present, that will be exposed to the UV light. When I already told that throughout this discussion I will consider the negative photoresist. Whenever the light falls on the negative photoresist, it will be hardened. Okay, so the light falls here on this one at this point and at this point, and here also and here also, right? So when the light falls, what happened? This region will be hardened, and this region will be hardened, and this region will be hardened. Okay, so this is about how you can use the photolithography, and at the same time how you can apply the UV light for the photoresist. Okay, so this is the next step. Next what we have here. So what we will do is, first we will remove whatever the unexposed photoresist and the SiO2 under it. Okay, so what I am doing in the next step, I am removing first unexposed photoresist and the SiO2 layer under it. So first I will consider here, I will remove this one. Okay, so I will remove this photoresist. Right, and the SiO2 under it. Right, so I am removing this photoresist and at the same time SiO2 under it. Okay, after removing that, what I will do is I am also removing the exposed photoresist also. Okay, if I remove that exposed photoresist, so what I will get like this. So after removing this one, so again I am removing this exposed photoresist. Okay, exposed photoresist. After that, what I am doing here is nothing but the SiO2 only will remains. Okay, at this point what I will do in the next step is nothing but I will remove the unexposed photoresist. Under it we have SiO2, that will also I will remove, so that there will be a formation of one well. Okay, so after that I will remove the remaining exposed photoresist also. So if I remove all these things, the only SiO2 will be present. That SiO2 we have here. Okay, similarly we can also remove this area also. Exposed photoresist means this area also we can remove. Okay, so now remove the unexposed photoresist and SiO2 under it, then exposed photoresist. Okay, so after doing that, after forming this one, after getting this one, what I have to do the next step. So I have defined the regions of N well and P well by using this mask and this mask. Okay, by using this mask and this mask, I have defined the N well and P well regions. Okay, but I have not formed this N well or P well. Okay, so P well means what? It consists of P type material, P type semiconductor material. Okay, N well means what? It will becomes N type semiconductor material. So I have to form, this is pure silicon, right? So this one is the pure silicon for us. Okay, into this pure silicon, what I have to do? So into this pure silicon, if I send boron atoms, okay, I have to form P well. So into that pure silicon, this epitaxy layer is pure silicon. Pure means intrinsic. Okay, into that intrinsic semiconductor, if I send or if I introduce the impurities of trivalent. Trivalent means what? Boron, aluminum, gallium and indium. So here I am sending these boron atoms to form the P well. So if I send these boron atoms to here, it is already a pure silicon. So if I send that impurities, that boron atom will make that pure silicon into P type. Okay, so that is formed is here P well. Okay, so what we are doing after this one is, after removing the exposed photoresist and unexposed photoresist under it SiO2, after removing that, I will send the impurities. I will introduce the impurities onto the epitaxy layer in our well region. Okay, where we are going to form this P well and N well, into that region I have to send the trivalent atoms for the formation of P well. Similarly, pentavalent atoms for the formation of N well onto the epitaxy layer or pure silicon layer. Okay, if I send these boron atoms onto the defined region of epitaxy layer, it will forms a P well here. So that is what here we have. Remove unexposed photoresist and SiO2 under it, then exposed photoresist, and send boron atoms to form the P well. So here it is already epitaxy, it is a pure silicon. If I send boron atoms into that, so it will become a P type material. So that region we call as that one as what? P well. Okay, so here like this we can form the P well. Okay, now what I am doing here, so I am repeating the same process whatever I have done for the P well. So I am doing the same process. That means what? Again here I am removing this first and SiO2 under it, so that it will forms a region or a space for N well. So now what I am doing here, I am sending the pentavalent atoms, that is phosphorus, suppose phosphorus atoms. So if I send the phosphorus atoms into the epitaxy layer or pure silicon layer, so it will also form the N well. Okay, N type material. So here if I send the boron atoms, it will form what? It will form the P well. If I send phosphorus atoms, here it will form N well. So both N wells will be, N well and P wells will be formed. By repeating the above steps, we can also form the N well. So that is the formation of N well and P P well. Okay, so here we got TwinTub means or twin well means here we have two wells, that is N well and P well, and those are formed by using these steps of fabrication. So here N well is formed and at the same time P well is formed. Okay, now what is our duty next? So we have to form the gate. Okay, P well means it will act as a P substrate, and here we are going to accommodate NMOS transistor. Okay, here N well means it acts as a substrate, and here we are going to accommodate the PMOS transistor. Okay, so in P well we are forming NMOS and in N well we are forming PMOS. Okay, so both PMOS and NMOS will require a gate. Okay, for the formation of the polysilicon gate, what we will do? Again we will form a thin SiO2 layer. Above that we will place the polysilicon, and above that we will place the photoresist, and that photoresist will be exposed to the UV light. That's what we are going to do. Okay, in all these steps, all these processes, N well or P well or NMOS, so we are going to do the same thing. First we will place the thin oxide, on that we will place the photoresist, polysilicon. Above that polysilicon we will place the photoresist. Okay, that photoresist is applied with the UV light, applied to the UV light. So that's what the next step after forming the N well and P well. So now we'll go with the polysilicon gate formation for both PMOS and NMOS that are formed in P well and N well. Okay, so next grown the SiO2 polysilicon, and above polysilicon grown a photoresist layer, then apply the UV light using the mask. Why we are doing this? Using the mask for the formation of gate. Okay, so here this is nothing but thin SiO2 layer or thin ox we call. Above that we have the polysilicon. Above that polysilicon I have placed the photoresist, and that photoresist is applied with the, that photoresist is exposed with the UV light. Okay, here I have to form two gates. Okay, so I have to form two gates. That's why here I am using this coating to protect the UV light to protect the photoresist from the UV light here and here. Okay, or we can also call to unexpose the photoresist by using this one and this one, and the remaining parts will be exposed. This part will be exposed, this part will be exposed, and this part is also will be exposed. So this will be hardened. Okay, these things will be hardened, and the remaining will be unexposed regions will be soft one. Okay, so now what we will do here? Okay, so what we will do means first we will remove the unexposed photoresist and polysilicon under it, SiO2 under polysilicon. Okay, so we will remove those things, and we will, after removing that, we will remove the exposed photoresist also, so that only the gate polysilicon and thin oxide here and polysilicon and thin oxide will be present. Okay, so this is how we can form a gate. Okay, after this one, so what we have to do is remove the exposed photoresist, polysilicon under it, then remove the thin ox under it, and then we have to remove the unexposed photoresist. So what is the first one here? Remove the exposed photoresist. So what is the exposed photoresist? This one exposed photoresist, and at the same time the polysilicon and SiO2 under it. So I am removing all these things. Okay, so if I remove that one, the remaining thing that is present here and here is also, it is also an exposed photoresist, and I am removing the polysilicon under it also. I am removing the exposed photoresist and the polysilicon under it. So next one here also it is exposed photoresist and polysilicon under it. Okay, so only the remaining is nothing but unexposed photoresist. So remaining material is what we have, unexposed photoresist under it we have polysilicon, under it we have thin oxide. Okay, so now what I am doing after removing exposed photoresist, polysilicon and SiO2, now I am also removing this exposed photoresist, unexposed photoresist. So the remaining present is nothing but polysilicon and SiO2, thin SiO2. So this will forms the gate for us. Okay, gate for NMOS and at the same time gate for PMOS. So that's what I have represented here. This one is the polysilicon and this is thin oxide. Okay, so after this what we have to do, right? So I have formed the gate. Now what I have to do? So in P well and N well we are forming NMOS and PMOS. Okay, in P well we are forming NMOS transistor, in N well we are forming PMOS transistor. So N well, NMOS means we have to place N plus regions for source and drain, and for PMOS means we have to place P plus regions. So for that one, again what I am doing here is, so I am growing SiO2, thick SiO2 layer. Above that I am using placing the photoresist. Above that I am using the mask to define the regions of N plus. Okay, so that's what I am doing in the next step. So grown the thick SiO2 layer and photoresist above SiO2 layer and exposed to the UV light using the mask to define N plus diffusions to form the source, drain and substrate terminals. Okay, so that's why here I am using this mask. This one is the UV light. What I am doing here, UV light, and this photoresist I am exposing to the UV light so that wherever the UV light falls, that will be polymerized and the remaining will be softened. That means as it is, it will be present. So I am placing this mask here and polysilicon, and this one is the SiO2, thick SiO2. So this is thin SiO2 and this one is the polysilicon. So now after falling that UV light, so what I will do after exposing that photoresist to the UV light, so here the we are blocking the light here and here. Okay, therefore this will be, we can remove easily, right? So after this formation of, after this exposing of your photoresist to the UV light, so now we will remove the required place, the photoresist, that is unexposed and exposed photoresistors. Okay, so now remove the unexposed photoresist SiO2 under it first, then remove the exposed photoresist and now diffuse the phosphorus atoms to form the N plus regions. Okay, so here what I am doing here, after doing this one, after doing this this exposing of this photoresist to the UV light, so I am removing first unexposed photoresist. Okay, so here I have unexposed photoresist, this one and this one, under SiO2 under it. So I have removed. Now here also we have unexposed photoresist for us, unexposed photoresist, and here also we have unexposed photoresist. Okay, so these are the regions, this one and this one and this one are the regions what we have to define. We have defined to form the N plus regions or N diffusion. Okay, so here I have defined the N regions, okay, for the source and drain and substrate. Now what I have to do? So to form the N-type material, what I have to do? I have to send, I have to introduce the pentavalent impurities, or we can use here for a particularly phosphorus atoms we will send. So now what I am doing is, I am sending the phosphorus atoms here into this place. So it is already N well. So if I send the phosphorus atoms here, so here N plus diffusion is formed, N plus, and here also N plus will form. So here P well means what? NMOS transistor we can form. So here source and drain is formed by this N plus and N plus. That's what the next step what we are doing. Remove the unexposed photoresist. I am removing unexposed photoresist and SiO2 under it. So I have removed this one and this one. After that also what we have to do, we have to remove this photoresist also. The remaining exposed photoresist we have to remove like this. Okay. So I have removed this one also. So what happened here? So the resultant diagram will be like this. So in that space what we have defined, so I will send the phosphorus atoms here. Phosphorus atoms, so that this becomes N plus and this becomes N plus and this becomes N plus. Okay. So this is the diagram for this step. Okay. So after that step 10 we have, after the formation of N plus regions, remove the remaining SiO2 also. So I am removing this SiO2 here. Remaining SiO2 I am removing here. Right. So that is the only thing that is remaining for us. Okay. So similarly, similar steps if you extend for the P plus diffusion also. Okay. So this is what, how you can form the N plus regions. Now, after formation of these N plus regions, okay. So now we will repeat the same steps to form the P plus regions. Okay. Because here this is PMOS transistor that is formed in N well, and here we have P well, and in this one NMOS transistor will be formed. So already we have formed that N plus regions. Now I have to form here the P plus regions. Okay. For that purpose, we will repeat the same steps what we have done for the formation of N plus region. Similarly, we will do that, but instead of phosphorus atoms, to form the P plus, we will send the boron atoms, that is trivalent atoms. To send that, there will be a formation of P plus, and here we have P plus regions. So all the regions, that is for source and drain for PMOS and NMOS, and at the same time the substrate contacts are formed. Okay. So this is about how you can form here PMOS in N well and NMOS in P well. Okay. So after this one, what we have to do, right? So we have formed the PMOS and NMOS in the N well and P well. Okay. So that is what we have done up to this. After that, what we have to do, we have to form the metal contacts, or we can also call as contact cuts. Okay. We have to place the contact cuts. For that one, what I am doing is, I am again growing an SiO2 layer on the wafer. So here now to form the metal contacts, grown thick SiO2 layer on the top and remove the thick SiO2 at the required places by using the hydrofluoric acid. Okay, to remove SiO2 or to etch SiO2, we are going to use the hydrofluoric acid. So after this step, what I am doing, I am growing this SiO2, thick SiO2. So this one is thick SiO2 layer I am growing on the above here. Okay. So after growing that, wherever you require the contact cuts, at that point only you have to remove the SiO2 by using the HF acid. So now what I am doing here, I require the contact cut for this N plus, this P plus, and for this gate and this P plus, and all those things, although we have N plus, P plus, and for this gate also we require the contact cuts. So at that region only we will remove the SiO2 by using HF acid. So where I am removing, so I required here the contact cut, here I require the contact cut, and here also I require the contact cut. So I am removing that SiO2 by using HF acid, and here also I require the contact cut. Here I require the contact cut, here I require, here also I require, here also I require. So in all those points I am removing the SiO2 by using the HF acid. So after removing that, the resultant diagram is like this. Okay. So this is the contact cut for N plus, and this is the contact cut for this P plus, and here also we have the contact cut for this, for these gates also. At that point we are going to place the metal. Okay, so here it is the, after removal of this SiO2 by using HF acid, the contact cuts are defined, and we have placed the contact cuts where we require, okay, to connect that one to the external connections. So after this one, what I have to do is now grown a metal layer on the surface by using the metallization process. So throughout this surface, so here throughout this surface I am growing this SiO2 like this, SiO2 like this. Okay, why we use the SiO2 means wherever you have the contact cuts, through that contact cuts we can connect the external connections by these metals. Okay, this metal, so metal wires. So that is why we are going with the metallization. Now grown a metal layer on the surface of using the metallization process. So if I grown that metal, so here we have the metal contact, so that will be like this. Here also we will place here and here. This is the contact cut. Here we have the contact cut, and here like this and like this. Okay, so if you place this contact metallization process, so that will be like this. Throughout this we have the metal. Okay, but where we require this metal means, so I require at this contact cut, I require at this contact cut, I require at this contact cut. In the remaining places I don't require the contact cut, that is metal. So in the next step what we will do, we will remove that metal where we don't require. Okay, so here if you observe this one, throughout this surface I have grown a metal by using the metallization process. Generally aluminum metal will be grown on this one. So I am growing this metal layer on the surface completely. Okay, so because of that, after that one what we have to do is, wherever you require the metal, keep that one as it is and remove other metal layer. So that's what I have to remove the metal except at contact cuts, and by doing the planarization we will get the actual structure of CMOS. Okay, so now what I am doing, I am removing this one. Here also I am removing this one, I don't require. I require at this point, so I am keeping that one as it is. Here I don't require, and here I don't require. Okay, so here also I don't require. So these are the contact cuts where we require the metal. Okay, so this is per N plus region. So I have the wire here, metal like this, and this is the gate, and at this point also for P plus. Okay, and remaining I have removed, and where the contact cuts is there, at that point only I have keep that metal. Okay, so here we require, and here we require, like this here we require. Okay, so here this one and this one will be the substrate contact, and this P plus and this P plus and this N plus and N plus are source and drain respectively for NMOS and PMOS. So therefore this and this will be gates. These two gates will be connected. At those gates we will consider our input. Okay, so after removing all the metal where we require, by keeping that, and if you do the planarization means here after placing the metal there will be up and downs on the surface. Okay, we have to planarize that one. So by using the planarization process, if you planarize the metal up and downs, so that will be obtained as like this. Okay, so if you observe this one, after removing the unwanted metal, so we will get the structure of CMOS like this. So it is what? NMOS, it is PMOS, sorry, it is NMOS, and this one is the PMOS. Okay, PMOS, here it is considered as the drain. Okay, drain, and this one as the substrate terminal, and at the same time here the two gates will be shorted. This gate of NMOS and PMOS will be shorted, and this will be applied as the input. Okay, next here we have the drain and source of this one is NMOS, and that is connected to the ground. The source of NMOS will be connected to the ground. The inverter circuit will be like this. The basic circuit of CMOS will be like this. So this one is the gate. So here we have the PMOS and here we have the NMOS. So here I have given that this one as VDD, okay, and this one as VSS or ground we can say, and both these will be connected. So this is the connection where we are applying this VIN. So this VIN is applied here. Both gates, this is the gate and this is the gate. Both gates are shorted and we are applying the VIN for that. Okay. So next here we have VDD and this one is the drain of PMOS. So this one is the PMOS and this one is the NMOS, and this one is the source of NMOS and this one is the source of PMOS and this one is the drain. And here we are going to take the V output. Okay. So the basic circuit of CMOS is nothing but an inverter, CMOS inverter. So here we have V out, the source and drain will be connected and both gates will be connected, and we are taking the V input and output is taken across the source and drain of the PMOS and NMOS respectively. So this is now what is the final structure for us, that is we have the CMOS fabrication by using TwinTub process or twin well process, and it is very advantageous and advanced method for the fabrication of CMOS. Okay. And the basic circuit of CMOS is nothing but here the CMOS inverter we call. Okay, that is it consists of PMOS and NMOS. Both are accommodated in on a silicon wafer. Okay, so this is what about the CMOS fabrication steps by using TwinTub process or twin well process. Okay, thank you for watching. Subscribe our channel.